Welcome to the Explainer. Okay, let's set the scene. Imagine you're sitting in the exam hall. The clock is ticking down, the invigilator is pacing at the front of the room, you turn the page, and boom, you are immediately hit with this massive wall of complex geometric shapes, coordinate grids, and vector notations. The deadline pressure is absolutely immense, right? We've all been there. This is the ultimate challenge of the Cambridge Mathematics examinations. But today, we're taking on a very specific mission. We are going to untangle these complex questions and deliver the perfect, full-mark answers. We'll transform these dense Cambridge O-level mathematics review exercises into clear, actionable strategies. You know, the clock is ticking down for students like Alex and Sam. When Alex sees a multi-part geometry question, he just panics. He dumps every formula he knows onto the page without actually analyzing what the question is asking for. And then you have Sam. Sam is fast, but he rushes, entirely missing the specific command word requirements that the examiner is actually grading against. So we're going to look at these flawed approaches, and I'll show you exactly how to avoid their mistakes.
Now, what's really interesting about these 2 pages from Review Exercise 8 is just how intimidating they look at first glance. If you just stare at this as one big block of information, your brain basically experiences cognitive overload. You're seeing a boat, a playing field, triangles on grids, vector ratios. It is just too much. And this is exactly where Alex freezes up and where Sam starts rushing blindly. But here's the secret. When you look at these 2 pages side by side, you are actually looking at 27 potential marks. In a standard Cambridge exam, missing out on 27 marks is literally the difference between an A star and a C grade. It's a massive swing. But what if we didn't look at it as one terrifying test? What if we looked at it as a series of highly predictable puzzles? The trick to conquering these pages isn't just knowing more math, it's knowing how to read the examiner's mind. We have to look past the diagrams and focus entirely on the command words. Words like calculate, express, and describe fully. These aren't polite suggestions. They are the exact blueprint for your grading rubric.
So to manage all that cognitive load, we're going to break the questions down into 4 specific mathematical domains instead of just reading them chronologically. We'll start by navigating spatial geometry, then move on to mastering visual transformations, unlock vector paths, and finally, look at the final mark tally.
Let's dive right into Section 1, Navigating Spatial Geometry. This is where we master bearings and elevations. Spatial geometry is where examiners absolutely love to test your ability to translate a real-world scenario into a strict mathematical model. They'll use words like bearing, elevation, and level playing field. These words are triggers. When an examiner says level playing field, they are explicitly telling you that we are operating in a 2D plane from a top-down view. That means standard trigonometry applies, and you don't need to account for any weird 3D terrain variations.
So when we look at high-value questions like question 2, we really have to ask ourselves, how do we extract the maximum marks without getting completely lost in the diagram? A 4-mark question is a massive red flag. It's telling you that you cannot just punch numbers into your calculator and scribble down the final answer. The examiner is explicitly assigning marks for your execution. Think about it. You'll likely get 1 mark for identifying the correct trigonometric rule, 1 mark for substituting the correct extracted values, 1 mark for the intermediate calculated angle, and only that final single mark for the correct bearing. If you rush straight to the final answer like Sam does, you might make a tiny calculator error and score 0 out of 4. But if you show your step-by-step execution, a calculator error might only cost you 1 mark, allowing you to easily secure 3 out of 4.
And this brilliantly illustrates our deconstruction technique. We're focusing our attention purely on the playing field in question 2, where AB is 65 meters, BC is 70 meters, and CA is 110 meters. Notice how much information is packed into this single quadrilateral. We have our side lengths, we have angles of 70 degrees and 58 degrees. We also have a vital piece of text, C is due south of B. Now, listen, this is where students often fail. They try to find the bearing of A from C by just blindly adding up internal angles without any reference to north. To find a bearing, we absolutely must measure clockwise from north. Because C is due south of B, the line CB perfectly aligns with a north-south axis. This means if we draw a north line at C, it is simply an extension of the line BC upwards. That single realization, that is the key to unlocking the entire problem.
The crucial point here is following these exact steps to bridge the gap between the drawn diagram and the actual mathematical calculation required for those 4 marks. Imagine the red pen marks of failure transforming into brilliant green check marks on your paper. Step 1 is identifying what you have. We need the bearing of A from C. This means we start at C, point north, and turn clockwise until we hit the line CA. To do this, we need the angle BCA. Well, how do we get angle BCA? We look at triangle ABC. We have all three sides, 65, 70, and 110. What rule do we execute when we have three sides and need an angle? The cosine rule. You state the cosine rule for your first mark, you substitute your values, 65 squared equals 70 squared plus 110 squared minus 2 times 70 times 110 times the cosine of angle C, that's your second mark. You solve for angle C for the third mark, and finally, because C is due south of B, your north line points directly away from B, meaning the bearing is simply 360 degrees minus the angle you just found. That is the final logical step for your fourth and final mark.
We can apply that exact same strategy to question 4. We need to recognize that the 32-degree angle of elevation of A from B is the vital key to finding angle ADC for another 4 marks. At first glance, what is the core trick hidden in this diagram? I'll tell you. The trick is that BCD is a straight line, and the angle of elevation of A from B is 32 degrees. But look closely, where's the right angle? It's at C. The angle of elevation is measured from the horizontal. Since BCD is horizontal, the angle ABC is your 32 degrees. Once you lock that in, you can use basic SOHCAHTOA in the right-angled triangle ABC to find the height AC. Once you have AC, you jump over to use the second right-angled triangle ACD. You now know AC, and the base DC is 6 centimeters, so you can find angle ADC. It's a 2-step puzzle, perfectly designed to test your step-by-step execution.
All right, shifting gears entirely. Section 2, Mastering Visual Transformations. This is all about decoding the coordinate grid. And let me tell you, this is an area where examiners report massive point drops, simply because students fail to use the exact terminology required by the syllabus.
By isolating the grid in question 5, we immediately see that we need to define the geometric relationship between these two simple shapes. Let's look at a classic flawed answer for question 5a, which asks to describe fully the single transformation that maps triangle A onto triangle B. A rush student might just write, it's a translation that moves up and to the left. Can you spot the exact reason this answer loses marks? The hint is right there in the command words, describe fully and single. While the shape didn't rotate or change size, meaning it is indeed a translation, this answer fails to use the language of mathematics. Up and to the left is geographical language. It's not mathematical evidence.
The examiner is looking for very specific details, like ensuring you only use a single transformation to map A to B, to earn the full 4 marks for the section. So how do we write a perfect paragraph for 5a? Your starting point is stating the transformation type, translation. Bam, that's 1 mark. Your evidence must be a column vector. Pick a point on triangle A, let's say the bottom right corner at -1, 2. Find the corresponding point on triangle B, which is at -5, 6. How do we get from an x of -1 to -5? We subtract 4. How do we get from a y of 2 to 6? We add 4. So to secure the second mark, you state the column vector exactly. Top number -4, bottom number +4. For part B, enlarging with a scale factor of -2, well, a negative scale factor means the shape goes through the center of enlargement and flips upside down, ending up twice as far away on the other side. You absolutely must draw construction lines through the center, which is 0, 3, to guarantee your accuracy.
Let's transition to our third pillar, Section 3, Unlocking Vector Paths. From simple expressions to complex ratios, vectors are often the final frontier for Cambridge students. They require you to think algebraically about spatial directions. Let's see where the visual meets the abstract.
Think about this comparison for a second. It highlights vital exam strategy. You must pace yourself differently for a quick 1-mark expression compared to a demanding 4-mark ratio calculation that requires clear working. On the left, we have question 3a, express vector AB in terms of A and B. It's worth 1 mark. On the right, question 3c asks you to find the ratio OC to CD, and it is worth 4 marks. You cannot spend 3 minutes agonizing over a 1-mark question. A 1-mark vector question usually requires a single visual path logic. To get from A to B, you just go backwards along OA, which is -3a, and forwards along OB, which is +6b. So -3a plus 6b. You're done in 15 seconds. The 4-mark ratio question, however, is where you have to deploy your full strategic blueprint, taking the time to show every single logical deduction. The very first step is to create a common unit on the outside of the brackets for each vector. Looking at question 3, we have to carefully extract the given vector paths. We note that OA equals 3a, OB equals 6b, and the ratio of AC to CB is 1 to 2. Now this is where we separate the A-grade students from the rest. The problem states the ratio AC to CB is 1 to 2. Listen carefully. This does not mean AC is half of CB in a way that makes it 1/2 of the whole line. No. It means the line segment AB is divided into 3 total parts. 1 plus 2 equals 3. Therefore, the vector AC is exactly 1/3 of the entire vector AB. That is the critical extraction phase. If you mistakenly use 1/2 instead of 1/3, you will mathematically destroy the rest of the 4-mark question. Once you have AC, you can find the position vector OC by starting at O, going to A, and adding AC. You systematically build your paths using the exact building blocks the examiner gave you.
Contrast that visual problem with question 6. Here, you are given strict numerical position vectors for point A at -5, 2 and point B at 7, -4. This is pure numerical extraction. To work out the vector AB from position vectors, the rule is always the position vector of the destination minus the position vector of the start. So vector OB minus vector OA. 7 minus -5 gives a top coordinate of 12. -4 minus 2 gives a bottom coordinate of -6. Then finding 3 ABs simply means multiplying both that top and bottom number by 3. Easy. Finally, part 6C asks for the magnitude of AB, which is indicated by those vertical modulus lines. This is basically a disguised command to use Pythagoras' theorem on your column vector components. You square the 12, you square the -6, add them together, and take the square root. Bam. 2 marks easily secured simply because you decoded the command symbol.
Finally, Section 4, the final mark tally, calculating your exam strategy. Let's step back and look at the actual tangible value of effectively deconstructing these 2 review pages.
When we organize the questions by category and mark value, we see exactly where we need to invest our time and effort during the exam. By categorizing the exam like this, you establish a real-time management matrix. Look at question 2. It's worth a massive 7 marks in total across its parts. That is exactly where you invest your deep, focused analysis. You make sure your cosine rules are written out perfectly. Meanwhile, question 5 on transformations is a really quick 4 marks if you just know the exact terminology. By mapping out the exam this way, you take control away from the examiner and put the power right back in your own hands. You aren't just doing math anymore, you are executing a high-level operational strategy.
All of those carefully extracted details and applied steps add up to a staggering 27 total marks available across just these 2 pages. 27 marks. Really let that number sink in for a second. That is an enormous chunk of your total exam grade just waiting to be claimed.
I hope this strategy session has shown you exactly why breaking down the source material step by step is the ultimate way to master your mathematics exam. You now have the real tools: command word decoding, strategic application, and time management. So, when you sit down in that exam hall, are you going to let the complex diagrams intimidate you, or will you use this categorical breakdown to systematically conquer every single mark?